Um, Hi, everyone. Thanks so much for coming to the talk. This is technically not a talk. This is a kidnap. You've been kidnapped. I really wanted to learn about this, so I decided, like, what is the best way of learning something? I will prepare a talk, and OK. 1, 2. Try. Testing. Hear me good? OK, cool. Gorgeous. OK, so I really wanted to learn about this, and now you're going to learn all together. I'm going to do this like old teacher thing of closing the door. Because I get distracted. OK, cool. Let's go. So the chat for today is myself. I'm Mike Giménez. I'm a research engineer at Google DeepMind. And what I've been working on, please, work. OK, and I've been working on this thingy. If the internet, OK, there we go. So I've been working in VO3 for the last year and a half, more or less. But the trick is I am not a diffusion person at all. My background is in language, but I was like, it's a transformer. How bad can it be? Turns out it's not that bad. But I was really looking forward to learn how these things work. There's audio, because we do audio, because why not? But yeah. You can check it out. This is the latest release that we've done, and it's very fun. So anyway, so the menu for today, we're going to have generative models. We're going to see a tiny bit of math behind this, diffusion models, and finally, we will implement it using, we are going to implement a very basic DAT, diffusion transformer. Basically, you have transformer that predicts noise. We're going to do it in JAX. And as a start, I have a little collab where you can try everything by yourself. I don't know if you had a chance to get the QR. I will put it at the end, if not, so you can follow it through. OK. So this is our boy bias. Bias have like this equation. I was like literally thinking like I should tattoo it, but it's like it's too basic. It's like too vanilla. But anyway, this is the main equation that goes behind all the cool models that you see. Discriminative models uses the posterior probability, basically, what is the probability of seeing an image of an animal to be a cat, as the internet, so high. And then you have the discriminative models. Discriminative models gets the likelihood and the marginal. So basically, what is the, if I want to get a cat, what is the probability of seeing an image of a cat? Or what is the probability of an image without any conditionals? Cool. OK, I promise you the intro to math is going to be very gentle. I'm going to take your hand, because I have the feeling like diffusion models try to hide things behind a lot of math. It's not that deep. So diffusion model has like this Markov chain, where it's like every step depends only on the previous one. And we have two processes, a forward process, where we slowly keep adding noise, and a backward process, where we slowly remove noise. Awesome. So the forward process is trivial. You increasingly add more noise, so you start. This is like the image-only fundamental paper. It bothers me a lot, because I think forward should go in the other direction. But you start from the image x0, and then you slowly, gradually add more noise until you end in isotropic noise, so basically random noise. The problem is the other way around. The other way around is unknown. And it's unknown because if you notice, it's conditioned on xt. xt is every possible image that you could have in the world. So yeah, unknown, untractable. And the forward, this is our boy Gauss. And our boy Gauss defines a Gaussian as the mean and the variance. And basically, we have, like, the forward is the easy part. It's the part where you have a schedule where you increasingly add more noise. You can have, like, you can think of like a linear schedule where like every step adds the same amount of noise. Or you can think like something like cosine. You can, like, wherever your heart desires. Markov chains depends, the previous step depends on the past one, on the previous one. The cool thing is, like, if you combine two Gaussians, you can go directly to any step that you might want. And this is what we can do. So we don't need to compute the time, the Gaussian time for every. the noise for every time step. Awesome. So this is the thing that we're going to implement. This is how it looks like. And simply, we compute all the possible alphas that we can get in our equation. And then we simply sample. Yes. You generate sample noise, random noise, and you add it to the image. And you slowly but surely get from the real image into pure noise. So this is the forward process. And the backward process, we're going to go the other way around. You want to get the image, you get a noise, pure noise, and you go back to the image. So this is the problem, right? As I was saying before, backward process is intractable because it requires knowing all the possible distribution of all the possible images, so no cute. But here, the machine learning people is like, don't worry, we got you. We're going to parameterize this probability, and we do it with this p, zeta, and zeta are the parameters. I always find like a little bit too fancy, but yeah. And what we're going to do is, this is a Gaussian, we're going to remove noise, so we predict the mean and the variance. In the first paper, only predict the mean and keep the variance constant. It was an identity variance. And then Sora came up and was like, you know what, we're going to predict both, and actually it's better. There's like a triple trampoline thing that will go from this variance into what we actually train on. It's proof, then it's equivalent. I'm not going to make you suffer through the mathematical proof, but if you predict the noise and you compute the noise versus the actual noise, then you know then it's on that step is equivalent. So you basically have the Kuba-Labor difference, the KL difference. Yes?
So when you're applying like the reverse process, you're also applying the Gaussian the same way as you are adding noise. So
yeah.
You are extending by also adding like
yeah, you predict it, right? Like when you go the other way around, since you cannot know exactly how much noise to remove, you predict a noise, and with the neural network then you have, like, you try to adjust.
The image transformation is still applying Gaussian to that image.
Yeah, removing. Yeah, it's like, yeah. This is the algorithm. So basically, you get an image, you compute what time step. So in a batch of our training, we are going to have any time step, like let's say you have 100 time steps that you want to predict. The more small the time step is easier, but then it's harder to sample, as you will see in the samples part, because we have, like, in a batch, you have, like, the step 1, 15, 17, whatever. It's very random, like, it's literally random. So you sample any time step, sample a noise, do gradient descent, difference between what you predicted and what you know expected, and that's it. That's easy peasy. The problem with sampling is now we cannot do, like, autoregressive generation. Like, this is how transformers normally, like, your ChatGPT, your Giménez, what we do is, like, predict the next step, and we're good to go, so it's very fast. So if you see Nano Banana, or I keep forgetting other people's models. If you see any image or video models, it takes a little bit longer, and it's because we do this loop. So you need to denoise every step. There's tricks, obviously. You don't need to denoise all the steps, like you can do distillation, RL, but the basic thing, you need to let it cook. Okay, this is the modern approach of how to parameterize this thing, because transformers won. Like, everything is a transformer these days. Before, just out of curiosity, we used to have a unit, which is basically you have a bottleneck, and you bottleneck, and then you open. Here's this DIT, predicting the noise. And I don't know if you're familiar with it. Let me do this. I was dying over there. Don't know if you're familiar with the Harvard lottery. Transformers have won the Harvard lottery. I'm always very skeptical of other architectures being able to be as efficient and as scalable as Transformer, because we have built in the hardware improvements for the Transformer. So why we do Transformers is because scale, global attention, and it's better handling of the conditioning. This has, like, the DATs work in the latent space, which means when we arrive here, we have, like, an autoencoder before, so there's another network that has gone from the pixels into latents. And then we have conditionings, and we're going to talk about what conditionings look like. We're going to implement this in JAX. JAX, if you know NumPy, like how many of you know NumPy? Yes, and you know JAX. It's easy. It's basically NumPy. Like I swear to God, like every time I try to do something new in JAX that I don't know, if I know the NumPy function, it's like, well, I'll try. Or most of the time works. It's functionals, transform code, and this is the 4 functions that you need to know. I will argue you only need the first 2, and yeah, maybe vmap and pim. Pmap is where basically grad computes a gradient, jits a function, vmap and pmaps parallelize at vectorize, batch level, and device level. So vmap is I'm going to go through in detail. Okay, this is what I meant. Like this is a very basic MLP. So you can see the weights, the biases. You compute the dot product between weights and biases, a non-linear function. Here we're using the time, and we're good to go. And as you can see, I literally only change the import line and change NumPy for GNP. So really, really trivial to implement. And I really like JAX because it gives you like a lot of control. OK, so this is what we want to do. We want to get gradients. We've said that we compute the gradient of the noise. And it's as simple as put grad into the function. I'm doing it like as a function here, but that's a decorator. And yeah, you can control which variables you want to differentiate against. And you can get the value and the value grad. Gorgeous. I feel I'm talking too fast, but yeah. If you have questions, by all means, interrupt me. I'm very excited to be talking about this. Yes. Yes, sure.
Yeah. What was the reason for using JAX instead of NumPy again?
Is jittable. Like you can jit these functions, and Sorry. Like the question, I can repeat the questions for the stream. The question was why to use JAX instead of NumPy. NumPy is not jittable, so you cannot jit the functions. There's no gradients for maybe, but yeah, it's not optimized for this. And this is like we have also talked on top of like frameworks on top of JAX to do all ML. You can, and I actually used to teach in school how to do backward with NumPy, but it's like painful, really, really painful, and you cannot JIT. So I think for that is like the main reason to use JAX. The jitter. So the jitter basically takes a function and compiles and makes it performance. So if you want to write for CPU, GPU, or TPU, you will need to write different domain-specific languages. We don't want to do that at all. So what we do is like we write JAX, and JAX does the tracing. So the type of jitter that JAX does is like it has a tracer and a compiler stage. First, they change the inputs for tracers, and then you have only the shape and the array. And then it goes through a tracing phase where you go through all the code, and then you see, oh, OK, I have an add dot and I have a ton, and if I can combine fuse operations, try to do it, and then once they go into JAX PR, then you compile into XLA. And that's the low level, like execute and go into compile mode and try to cache as much as they can. The cool thing here is like you can see, then we put JIT into a function that we want to JIT.
And that JIT function works like out of the box, or it needs to do some optimization, it takes a bit of time?
Yes. The question is like if jitter works out of the box. It does. I'm glossing over some details that's like somehow wavy. It sometimes might not work. XLA has bugs all the time. JITting is hard, like really, really hard. But in general, like if you want to do something like training an MLP, it will work out of the box. You don't need to do anything special. Cool. OK, now vectorization and parallelization. Obviously, all of the things that we've been talking about is matrices. So we need to be able to very efficiently work with matrices. And then we have vmap that works on batches. So you tell the function like, hey, I actually want to JIT with VMAP, and they try to JIT with VMAP. And then PMAP is like these devices do not fit in a single machine, so you need to distribute this. Sharding is the pain of my existence, so I'm not going to tell you how difficult it can be. It's like a dark arts. Like some guys at Google put a tutorial online that I highly recommend. It's like how to scale your language model. But it's a science, so it's also very, very dark art. But you need to be able to spread your model params and your matrices across different devices. OK. And since we don't want to be working in this low level all the time, we use Flux. So JAX is functional. Everything needs to be pure. And I feel like scientists and engineers, we are not the best at working. Well, it's not the thing that we do regularly. So we like object-oriented, and Flux gives us object orientation. And this is the thing that we inject everything. I think like now I write class and I immediately inherit from an X model. But basically, it's a model that represents a model. And it does it in an object-oriented. Since the functions need to be pure, and pure means all the outputs are only affected by the inputs, no input-output, and no side effects, we need to purify all the functions. And the way that we do it is using pytrace. So all the functions are pytrace. And I'm now thinking I had a JIT error, and it's because it's not the pytree. And pytree is a glorified tree where the leaves contain the actual values of the things, and then we have all the structure in this argument. And we know how to JIT this thing. OK, and this is a very basic example of what Flux looks like. They have like some built-in, like you obviously don't need to do drop norm, batch norm. Like there's like, I think we have MHAs as well. So there's like most of the things that you want to use to build your model is already here. So you can see like you have an X module, and then you can call the function, and when you call it, it executes wherever you want to execute. It had support for optax. Optax is the library that we use for optimizing. Groundbreaking. And yeah, it's functional, it's directly object-oriented because it transforms the module into pure functions. OK, and I have this question on Python, so I feel like I need to do this. I am not an expert on Torch at all, so I asked Giménez, pretty please, tell me the differences. So here, I verify most of them. I can tell you that the Flux column is correct. Basically, one of the drawbacks of Flux is that it's object-oriented, which means, no, the opposite. It's functional, which means debugging is painful. It's pure, so we cannot. There's a JAX debug print, then sometimes wants to work, sometimes doesn't. The cool thing of Torch is actually eager, it's functional, so debugging is easy. You will hear then it's not performant, but Meta trains very big models with PyTorch, so I will take this with a grain of salt. Anyway, this is the thing. Choose your hammer. My hammer is Flux. And this is the thing then we're going to implement again. First reminder, so this is a DAT, and we are going to go now slowly through all the blocks. I'm a very visual learner, so I like to implement exactly what I've been told, and we are going to see how it's implemented in Flux. So first of all, we batchify. As I was saying, these models work with noisy latents. So basically, I love like this, like Sander said this, like the latents of a decoder of the transformer are latents with attitude, because if you try to decode the latents, you can see some structure of the actual model, so it's of the actually video or images. So it's not super downsample. So an autoencoder, you bottleneck, and you use that small representation to like simplify your representation. And it's trained with with a representation loss metric. Don't want to go into the autoencoder. It could be a whole talk. Anyway, we have a vector that corresponds to the image in a small space. And then we want to batchify it, unify it, because text is a line of text. So what we do is use convolutional networks to apply this thing. So we go from the, let's say we have 32 times 4 channels on the latents, and then you go to the tokens. And this is a very humble convolution. So you say, where's the hidden layer? Where's the kernel size? You want to have non-overlapping, so valid. And then you reshape it. You make it straight. And then you need to add embeddings. You need to add positional embeddings, because otherwise you have lost. Like, if you split an image, like, the simplest thing is in 4 quadrants. So you need to remember that this quadrant, once you split it, what is the order of the pixels? So you add the positional embeddings. It's like a humble sum. And then you add some dropout. OK, so we have our latents over there. We're going to let it rest for a bit, and we're going to go into the right path. So the class embeddings, let's say I want an image of a cat. So we have, we go from the discrete variable into a continuous variable, so we can train on it. So we use humble embedding and then an MLP. Both will use a 2 layers MLP. And this is just it. So we get the embedding. So we say how many embeddings we want. So we want, let's say, I want my MNIST 10-digit class into 256 embeddings. So the vector is 256. You use the embeddings. This is a very classic sinusoidal embeddings. You put the 2 MLP layers, so dense is the MLP. In this case, we're using yellow. It's better. It's more stable. This is part of the dark magic. What nonlinear function use? Yellow is better. And again, we're going to do exactly the same thing for timestamp embeddings. So we are going to put positional embeddings, encode them, and sum them. So this is slightly more wiggly, because we need to get the embedding in 2 parts, and we want to have casino. So it's like this is slightly more tricky, but beyond the creepiness. Also, I type annotate this like a lot. I'm a firm believer. Let me show you the. Well, I will show you the next one that is a slightly better type. Or maybe, yes, let me show you this. Let me go back to this thing. I'm a firm believer in using JAX typing for absolutely everything. So this is extremely useful to catch arrays that are not correct. And it helps you a lot to know exactly what your inputs and your outputs are. For example, in this case, I know I'm going to have a vector with size but, the first. So the outside is the integers. I'm going to have an array. It can be a NumPy array, JAX NumPy array. It can be anything. Array is the general one, so it covers a couple of them. It is important because sometimes you have parts of NumPy, parts of JAX, and sometimes if you want to, sometimes it behaves slightly different. And I know that the output, since it's an embedding, is going to be a float, an array of floats, and the size is but hidden dimension. And if you're trying to, sometimes I put it also in the variables because I want to know exactly what I'm doing. And in this case, it was that's why I did it, because I wanted to know exactly what parts. Yes? Yeah. Yeah. Basically, here I wanted to know exactly what part was the sinusoidal, the cosine, and that was useful for me to know which parts you are going to have a mic behind. No.
It's just a quick question because I'm curious. So you can put in the tab annotations any variable you want, and it's going to keep track of the dimensions and when you're processing it.
It's within the JAX typing function. So there's a JAX typing decorator that I'm avoiding here. But if you put it in all the functions that you want to keep track of JAX typing, it will tell you if you have a JAX typing error. If you expect, let's say you split the batch or the hidden dimension, you expect, you're going to sum to, this is actually a good example. We're going to sum the timestamp and the classes, and if for some reason I call h in one and h1 in the other, and those 2 variables don't match, it will tell you there's an error. It can do operation as well. You can say, the output is twice the input size, so you can do the input is B and the output is 2B, something like that.
And the library does it out of the box. You don't need to install anything else. Or?
You need to install JAX type in, and
Okay.
it relies. We use beer type, but you can use any other type checker. But yeah.
Thank you.
Please type your things. It makes me happy, and it will save you a lot. Like, don't get me wrong, I understand. I understand that typing is more keys than you need to type, but I'm going to steal this up from Pablo. Like, you bought a very expensive keyboard. It gives you ASMR, so use it. OK, so this is the DAT block. This is the core of what we're going to do. Basically, it's a DAT block because you have a multi-headed attention. So instead of like having a two-tower transformer, you only use the multi-headed self-attention. So basically, an MHS. And then we have like a couple of cool things. The adaptive layer, I'm going to talk a bit more in the detail, but you have the conditioning, and we're going to scale and shape the transformer. I'm going the other way around. There we go. OK, so this is the ADA LN. It's very funny. The authors try a lot of things, all the normal things like condition on the, like using the cross attention to condition on. Nothing worked better than this. So this is what we go. Basically, you take the condition that you have added, and then you split it into scale and shift for the MHS, MHA, and then you have another scale, then you add at the end of the scale of the MHA. And this is implemented as simple as this. So this is the DAT block. I'm keeping everything. So basically, we have the conditioning. We split it into the alpha, beta, gammas, the first one and the second one, so the one for the MHA and the one for the dance or the feed forward. And then we broadcast. This is broadcasting exactly as NumPy does. And we apply it, so you can see the H1 norm after the layer norm. Then you modulate it using adding the gamma, 1 minus gamma plus beta, and then you apply the tension. Same story with the MLP. I know this is a lot of code, but I swear it's not that hard. Cool. And then we have the DAT. The DAT is simply stacking everything together. So we have our patch file. We have our embeddings, yellow time embeddings, and our class embeddings. We're going to add them together. And then we are going to rinse and repeat DT blocks, so we can have depth. I skipped the configuration of the DAT, but there's like a lot of dark magic of like the shape of your transformer, so your depth and your number, like depth and width, the other way around. Finally, after your DATs, you put your final output with a layer norm, and then you have your noise. You have your latence, and you need to amplify. So we go from this thin line into an image again. Obviously, this is it's not an image. It's the shape of an image, but it's actually latence. So for actually getting the image, we will need the decoder. So as you remember at the beginning, we have an encoder, which has a decoder. So when we train our encoder, we use the encoder to get the latence, the decoder to get the image back. Cool. And this is the diffusion loss. As we said, we have our alphas to get the noise at that time step. So we get the noise, we get the predicted noise, we apply the parameters, and we compute the scale. So basically the distance between the predicted noise against the actual noise. And this is the purification of the function. Funny thing, I completely forgot yesterday, but the things that you don't want to purify needs to go at the end. So actually, I haven't updated this. Alpha comes sum needs to be at the end, because otherwise I could not purify, because it takes everything after its positional arguments. So you need to put everything that you want to have fixed at the end. And this was the jitter error that I was getting. And this is the purify function. As you can see, we have the models, and just I pass the alpha cam sums. Cool. And finally, training. So we have we take some noise. We take any time step. We apply the normal, and then we apply value and graph we have the function, so apply the function, get the loss, get the diffusion, and that's it. It was very simple, right? Okay, let me go into the collab so we can. Let me go into the collab. Can I? Okay, this is a slightly bigger. You're not saying anything at all. This is too much. Okay, so as you can see, I need to import JAX. I need to install JAX typing for this to work. Multiple diffusion, and then we have this is our linear schedule. So this is how we're going to apply the. This is a little bit too big. This is how we're going to apply the noise. And then we have, this is our alphas. So this is the alphas that we see at the beginning. You can see like we are just summing over the betas, and then we apply it. This is the code that we see before. And then you can see like if you forward the process with the image on these time steps, you get into the noise function. Depending on how steep the betas will be, like I went to very low noise, so the image was still visible. You could have like gone deeper. Cool. This is the parameterized backward process, time steps, and you can see like I like to type text my things. I know exactly. I was learning, like I literally was learning about this with you guys. So I was like, let me see exactly what I got. Same with the embeddings. So you can see here, this is embedder, and this is the class embeddings. Input and outputs, we want to make sure that the outputs are correct, what we expect, because otherwise I implemented the MHA because fun. And finally, sorry, it's not my time right yet. Cool, so this is the DIT block that we saw before. We split, we apply it to the self-attention, to the MLP block. We test it again. And the DIT. Try not to do what I did here, because this is like all the possible configurations are done here just because I want to do it quickly. But try to be slightly more organized and know, like, because otherwise, like, you might want to change. This controls the autoencoder, this controls the model, this controls the MLP. So you probably want to aggregate them into pieces because it's easier to work with. And then, what is my class? This is my conditioning class. Well, I was testing here the diffusion loss, and everything is as expected. Yes, okay, this is the last thing that I wanted to talk about, and then you can ask me any questions. Configuring this thing is hard, and everybody tries to figure out a way of configuring their models in fancy ways. Data classes work. Just have a makeable data class, but try to make it not a massive thing. There's some logic behind these things, and if you want to modify it, like, I mean, the autoencoder, the depth, the shape of the model, like, try to make it in a more nicer way. Yeah, this is how you train. This is the training part. Yes, this is the training part, and we're good to go. Okay, this is the end of the talk, and I have, like, if you have any questions, anything that you want to ask me, I'll be more than happy to go through.
Questions?
Thank you very much. That was super cool.
I can ask. You can ask me in any language your heart desire, by the way. Okay.
Does anyone need English?
Go for it.
Spanish,
Go for it.
Para las anotaciones de tipos, estás declarando los tamaños de los arrays que estás recibiendo ahí dentro de un string, ¿cierto?
Sí.
¿El chequeo de estos tipos pasa en runtime cuando se está
Runtime.
ejecutando ¿O hay alguna forma de ejecutar, de hacer ese chequeo
As
estático?
runtime. JAX typing is runtime.
Entonces, cuando ya se está ejecutando, ahí te dice como, estas dos cosas
Sí.
no
Además,
tienen
es un-
match, y ahí es que, ok.
Es un poco la interacción de JAX typing y el jitter es un poco graciosa porque pasa después del tracing stage. Entonces, la discusión siempre ha sido que esto añade un poco de carga computacional porque cuando estás haciendo el tracing después tienes que hacer el chequeo de tipos. Mi argumento, yo soy la persona que ha puesto esto y estoy muy cabezona con eso. Mi argumento es que va a estar ejecutando semanas, so puedes esperar 5 minutos.
Sí, sí.
Pero sí, además es guay porque te controla que no hay nada inesperado.
Claro. Muchas gracias.
A ti.
Next one, please, in English for English speakers, okay?
Yes, sorry. So sorry.
Adding to the previous question, so it does not work while you're programming. You need to run it first in order to be able to check those types and the calculations.
Yes. So like when you're going to execute the program, we'll do the check. It will not, like, you cannot run MyPy and it works out of the box. I haven't run MyPy in ages. Like the way that we do it is we always, like Google always adds the checker into before check. Like you cannot do it directly. But yeah, it's always like you're going to execute your program. That's why you write it.
Any other?
You know if JAX allows a sprite optimization or something like that?
Sorry, could you repeat again? I didn't catch that.
You know if JAX allows a sprite optimization or something like that, for a sprite matrix and a sprite calculus, something like that, or
Yeah. So the jitter is, you get the advantages from the jitter because since you jitter the program, it tries to fuse operations, make things like slightly more performant. And then if you're going to have like operation across devices, it will put the operation on the device. So it has two advantages. One, the jitter will help us for a lot of things. And secondly, we don't need to write a different thing if we want to write in TPU. So most of the trainings is obviously in TPU. But if we want to serve this in GPUs, we don't need to. Because it's optimized, the code is optimized for any target device. So you have after your JAX tracing, you write, JAX writes the JAX PR, and then JAX PR at that stage, it has like a computational graph. If you're familiar with TensorFlow, it's exactly the same thing. And it's funny because sometimes there's TensorFlow in it. So we have a computational graph, and that computational graph, it's compiled for the device. So then it goes from JAX PR into XLA, and that stage is where you optimize, like if you have TPUs, you optimize the computational graph for TPU. If you have GPUs, so on and so forth.
Okay, perfect. There is time for one more. Any other?
Hello. Thank you for the talk. I just had one small question. Increasingly, we're seeing like autoregressive models for like image generation and so on and so forth. In your opinion, what is the driving force behind the fact that it's increasingly gaining in popularity?
The lottery hardware. We optimize for autoregressive. And obviously, like if you're serving Google or OpenAI are serving both models, having a single infrastructure to serve autoregressive, it's better. Block diffusion works better, like having diffusion still works better. Meta released a paper called Trans-Diffusion where there's like a lot of efforts doing autoregressive image generation. Meta has like this paper Trans-Diffusion where they do autoregressive both text and video. And Giménez, which is an internal effort, the video game generation model, that is autoregressive, so it's definitely doable. But if you think about the difference between Vue and Giménez, we have the video quality is better still in autoregressive, in diffusion models. In block diffusion models, to be fair, diffusion can be autoregressive as well. But yeah, it's the hardware, it's the implementations, yeah.
So it's time.
Okay,
Thank you.
awesome. Thank you.